Our next speaker is Dariusz Max Adamski, who is also an undergraduate student at PUT and also a proud member of our group. Currently, he is working as data scientist at Ecotherm Complex. Last year, Max was also a speaker at our conference. His talk was very interesting, so I hope that this year you will see also a very inspiring talk.
Hi everyone, thanks for coming to my talk. Today I'll be talking about probabilistic models, how they work, how to create them, and what they can be used for. I work as a data scientist at the Ecotherm Complex. I'm also a GHOST member, and I'm an undergraduate student at the Poznań University of Technology. So, without further ado, let's begin. But first, I want to talk about why I've chosen probabilistic models for my use case. At work, I analyze buildings with lots of smart meters. So we measure things such as temperature outside, inside, heating, cooling, sunlight, and many more. We want to use those measurements to perform actions that increase energy efficiency of this building, so that the owner may save money on heating and cooling and become more eco-friendly in the process. The first problem that I needed to solve was to analyze the effects of actions, and we can do this with causal probabilistic graphical models. We also don't really care about predictive performance of the models, so we don't need to predict the temperatures because we can measure them. But I really want to accurately model the dynamic system that is this building. For example, its thermodynamic state. And to do this, I want to learn a parameters of the function from the meters, from the values of the smart meters to the resulting temperature inside. I also know some of the parameters that I want to learn because the experts at the company I work for can compute them analytically with some margin of error. And Bayesian inference, which is the heart of probabilistic models, allows me to do just that, just specify the expected mean and the standard deviation of the parameters I want to infer. I also know that observations are noisy, and I know that the estimations of my models aren't perfect, so I want to report the uncertainty to my client. I know some of you will probably know this, but I want to do a quick refresher on Bayesian inference for those who don't. Let's say your friend offers you a bet. You will be tossing a coin. If they flip mostly heads, they win, and if the otherwise you win. So you say that they're your friend and you trust them, and sure, let's flip your coin. So 5 coin flips later, you say that, oh no, I have such bad luck, I'm losing right now. And 5 coin flips and only getting tails, you're losing for sure practically. And you are now, I would be progressively more wary towards the fairness of this coin or my friend's intent. And after 20 identical coin flips, I would be screaming to give me back my money because this game is rigged. This kind of updating beliefs in Bayesian inference is called a Bayesian update, and we update our beliefs before seeing some data are called prior beliefs and are described by prior distribution. And after seeing some data, we update this distribution to get our posterior beliefs, which are described by a posterior distribution. Here, initially we thought that the coin was fair, but we ended up, after seeing the data, thinking that it is most likely rigged against you. Now, mathematically, we update our beliefs with the Bayes theorem, and I rewrote this in a different notation, and this is the interpretation. So our posterior beliefs are proportional to the likelihood of the data given our prior beliefs times our prior beliefs. And in action, it looks a little bit like this. Consider a coin flip, but this time the coin is fair. And on the left side, we will have a distribution that has initially, we thought that it is equally likely that the coin only flips heads or tails, or it is fair, which is a bit ridiculous because on the right, I have a prior that says that most likely the coin is fair, because how many fake coins there are in this world, to be honest. So we flipped the coin 5 times, and we only gotten heads. And from the pure data, it seems that the coin is rigged. And the distribution with no information transformed like this. It says that it is most likely that the coin only flips heads, but the distribution which had more information progresses more slowly. It still says that there is some probability that the coin is fair. Now, after 20 coin flips, the more informative distribution has an easier time converging towards the true value. It has smaller sigma, and it is more on-centered than the uninformative prior. And now the posteriors, after 400 coin flips, converge to a true value. So as you can see, even if the priors aren't the best, with enough data, your probability distributions will converge to a true value. But if you don't have lots of data, and if you don't have lots of data, make sure to choose your priors wisely, because otherwise your results won't be good. Now, practically, we can implement probabilistic models with probabilistic programming, and a probabilistic programming language or library basically allows for this, with some extras such as abstractions like functions and classes known from programming languages, and also such systems provide all the probability distributions you would need and automatically perform inference for you, so you don't have to calculate anything. We'll do our first probabilistic program, and this will be a simple linear regression with one variable. You'll see how easy it is to create a probabilistic models and run inference. I've chosen this small dataset, which is an excerpt from the well-known iris dataset, and we'll run a regression on the sepal width and sepal length. Linear regression is most often written like this, but I'll use this notation from now on for my probabilistic models. And this basically says that points on the y-axis are sampled from a normal distribution centered on the value of this line, and with some standard deviation sigma. And standard deviation sigma is a positive, non-negative value sampled from a normal distribution, from a half normal distribution with some large standard deviation. This is called a weak prior because it is quite vague. And for A and B, the slope and the intercept of the regression line, we will provide no assumptions, so that the probability of each value on the real line is equal everywhere. This is also called an improper prior. Writing this model in PyMC is quite simple, as you can see. One thing to notice is that PyMC doesn't you have to pass standard deviation and not variance into your distributions first. And we set the observed value to our true values on the y-axis. Now we just call the sample function, which infers the parameters of our regression. And does 2,000 samples of them, and this basically results in 2,000 linear regressions from a probability distribution of A, B, and sigma. And this is the mean regression line, and all the others in green. As you can see, there is some flexibility in the slope and intercept, and a single point estimate doesn't really capture this uncertainty. We can inspect our model with tracing the plot, plotting the trace, which contains all our simulation or all our simulated lines. Here you can see that there are the parameters and their distributions, with most likely values being here and here and here. And on the right, we have values that the parameters had during the consecutive steps of the simulation. And it is very good that this looks like a fuzzy caterpillar. And the values don't jump around too much, because if they jump around too much, your model won't converge, and you'll have to either reparameterize it or run the simulation for a way longer time. We can also inspect convergence by looking at the R hat statistic, which would be close to 1, and we can see all the parameters in a tabular format with the summary function. Now, this is not the end of probabilistic modeling. We need to, after criticizing the model like we did just now, we can model the phenomena again and infer and criticize again until we're satisfied with the results. Now, there are tons of probabilistic programming languages and libraries. I've shown you PyMC3, but there's also Stan, and which is less general but also pretty pleasant, and Pyro, for example, which has support for some form of deep learning. Now back to smart buildings. How would we model a building? Well, I've chosen the approach of a causal probabilistic graphical model, or PGM, where each node in this graph is a random variable, and each node has children. Children of nodes are the parent nodes are assumed to be causes of their children nodes. So outside temperature, sunlight, heating, inside temperature, windows open, and user inside directly cause the inside temperature at the next time step to change. And heating, for example, directly causes energy usage to rise. Implementation of this graph in PyMC is easy. Each node, it's just a random variable. I've chosen a normal distribution centered at some discrete Python function, which could be a linear relation from the parent nodes or something more complicated. And we also have to pass some standard deviation, which can also be a function on random variables. Now, we want to change the future by choosing actions with the most desirable effects. So how do we analyze causes and effects? To show you this, we will consider an even simpler causal probabilistic graphical model. This model basically says that users inside cause the numbers of windows open to change, and both of these variables cause the inside temperature to change, because users inside exert heat from their bodies, and windows open also change the temperature, obviously. One way to analyze causes and effects is conditioning, which is akin to seeing. And if we see that windows open is the number of windows open is 0, we can now ask how our beliefs about the number of users inside of the inside temperature change. Now, this is very easy to do in Pyro, and PyMC not so much, because you have to rebuild the model. So I will use the Pyro notation, which is do Pyro condition our with this data. And then we trace again, and we can compute what we want, the values of these queries, by inspecting the trace. And this is the trace of the energy usage before conditioning, and this is the trace of the energy usage after conditioning in orange. We've chosen a arbitrary threshold k, and now we can compute the probability that the energy usage is lower than some threshold k if we saw that there are no windows open. This is just this integral, which is easy to do with a built-in function into a probabilistic programming language. Now, there are some pitfalls of conditioning. And for example, if I close all the windows, this shouldn't change my belief about the number of users inside the building. But conditioning does just that. So we need another tool. And fortunately, someone thought about it, and it exists. It's called an intervention, and it is akin to doing. This is written as the do operator, invented by Judea Pearl, and it basically says that if I force the number of windows open to be 0, for example, if I personally close all the windows, this won't change my belief about the number of users inside the building, because belief propagation in the graph is blocked from the node with the intervention to its parents. So this won't affect this if I intervene here. Now, interventions are analogous to conditioning in Pyro. We just do, instead of condition, we just write do. And trace analysis is the same as conditioning. So after analyzing many hypotheses, we can select an action that will, for example, reduce energy usage the most, and actually execute this action in the real world. So hopefully our models were right, and we've changed the future. Now we can make our models more accurate and even more interpretable in the physical sense by actually using physics thermodynamic equations inside them. For example, the experts at my company, the company I work for, constructed physical models of the buildings I work with, and each model is represented by an RC circuit. This is the RC circuit analogy, and it is useful because we can use the math already used in electronics to create a differential equation, to write differential equations that describe different states. And states are basically either, for example, measured temperature inside the building, or temperature in the envelope, which we can't necessarily measure. There are also other components in this model, such as the heat capacitance inside, or the heater, or the solar heating and the resistance of the walls, and the temperature outside. But we really want to infer parameters, which I selected in green. So the resistance, the capacitance, and the coefficient of solar heating. Now, to model such a stateful system, I used a Bayesian state space model, which at each time step has some control variables and some true building state and noisy observations. This is similar to the hidden Markov model, and the transitions between states are achieved by some transition matrices, A, B, and C. Now, the model can be written in the notation I've shown you like this. So the nth true building state is sampled from a normal distribution centered at transition matrix A times the previous true state plus transition matrix B times the current control variables with some uncertainty. And our observations are just sampled from a normal distribution of the transition matrix C times the true state with some noise. Now, deriving A, B, and C isn't very fascinating, but when you have differential equations, you can convert them to you can discretize them, and this is the key point to see. If we write a differential equation like this, we can substitute dt and solve for a, b, and c. If xn equals this, we can also use this equation to compute a, b, and c. C is trivial because we only want the value of the first state, and we want to discard the second state in the observation because we actually don't observe this. Now, the natural implementation of a Bayesian state space model is a for loop. And unfortunately, PyMC doesn't do optimization of the random variable graph. So we have to vectorize this. And don't worry, of course, if you don't get, you can't get this code in such a short amount of time. But we use a class to modularize our model so that we can use this whole Bayesian state space model just as we would use another random variable. Now let's fit the model to a few days of data. The temperature inside, outside, heating, and sunlight, amongst others. And we can draw a predictive simulation. In black, there are true observed values of the temperature inside, and in green, there are the confidence intervals of our model, of the simulation of our model. So you can see that it fits pretty well. We can also see how uncertain the model is about the predictions. But more interestingly, let's read out the parameters of the building, and we can easily do this with the trace plot. See, for example, the most likely value for the capacitance is here, and the sunlight coefficient is here. And we see that the model has converged very nicely. Now, we can use probabilistic models in a live fashion. So we can use our initial priors to fit our model and then produce a posterior, and then use the posterior at a later date to refit our model and get a next posterior. So I've heard someone say today's posterior is tomorrow's prior, and you can see how this can be used in deployment. I hope it will work pretty well when my company deploys these models for live use. We can also get anomaly detection for free because we can check at each time step if the posterior changed from the prior in a significant way. Now, I know smart energy is not the most interesting for everyone, but there are also great use cases for Bayesian state space models, such as for epidemiology, like SIR models and others, and other dynamic systems. Now, wrapping up, you've learned how to model the system and not the data with probabilistic models. express expert knowledge, analyze causes and effects, quantify uncertainty, and in my opinion, most importantly, move towards more explainable and possibly fair AI. Now, I didn't mention that you can use deep learning in the Bayesian mindset. This is easy to do both with Pyro and PyMC, so look into it if you're interested. There are also mixture models, Gaussian processes, more advanced causal inference, and more efficient sampling algorithms for big data problems. I hope that I've interested you. I've given you some interest in this topic, and you will look into it. Thank you for your attention. Here are the references and attributions, and I'll see you in the Q&A session. Thanks.
Thank you for the very interesting talk. I'm very happy that in the topics of the presentation during the Ghost Day, there was at least one presentation about Bayesian methods. They are not very popular in our Polish community, even though clearly you showed that they have many advantages. Some people claim, well, I think that it's kind of true that they are more computationally demanding. How this looks in your application? Do you have some problem with computational time? How long does it run to train your models?
For simple models, like the two-state RC circuit model, it's not so bad. Computation sampling time is about 10 minutes or so, so definitely lower than deep learning, and it learns what we needed to learn in a quite short amount of time. But if you have more hidden states, for example, in the hidden Markov model models, it could take up an hour or even longer. So the more variables, yes, they influence the execution time largely.
Thanks. Okay, and the question from the audience: how many variables can such model handle to keep a reasonable execution time? Well,
yes, I answered this basically just now, but in the first causal graphical model I've shown you, there was 10 random variables or so. In reality, we have a bit more, but this model converges very quickly, not even 5 minutes. But if you have a for loop somewhere or a vectorized operation, the sampling time will go up dramatically. So yes, we still need we have to use the ADV sampling algorithms. We can't use the better, the nuts algorithm I didn't talk about.
Yeah. Well, you also you mentioned the visual inspection of your model,
yes.
If it converges or not. But I suppose that they are like other methods. Do you use some of them?
Yes, I've also talked about the R-hat statistic, the Gell-Mann-Rubin statistic, which should be close to 1, as I mentioned. But the visual analysis is my personal favorite. It is very easy to explain to management and show them how the model actually works. And if, for example, your model doesn't converge, you won't have nice Gaussian parameter distributions, but it will be they will have very weird shapes.
Sure.
And also, you should do a posterior predictive simulation besides that to see if your model actually fits your data at all.
Sure. Okay, and you also mentioned that Bayesian methods can help us in building a more, let's say, trustworthy, explainable AI systems,
Yes.
which is kind of related to our previous talk.
Yes.
Could you maybe just a quick comment on that?
Well, if you design your models like I did, we basically design the system and not find random correlations. So you can make your equations explicitly not to include some information. And of course, you have to deal with hidden correlations in your data. But if you design the system the way you want, you can make the model think like you do.
Yeah,
You just basically design the world in your model, how you want the world to look to the model.
Yeah, and you can also include expert knowledge in the model.
Yes, of course. If you don't want, if you want some parameter to be very small, just include this in your prior. You can manipulate the well. If your prior is wrong, if you have lots of data, it will be overruled basically. But you can still influence your models a bit.
Yeah, I also think that there is like one other thing that Zuzanna, for example, the methods which Zuzanna showed are basically methods which allow us to explain the prediction. So, for example, which feature influence the output of the model. But on the other hand, if I have a model which gives me some prediction, and it is enough to change, let's say, one feature just a bit to change the classification, the question is if this explanation of this prediction is like trustworthy, is it worth it? And with a Bayesian method, probably we can measure better the uncertainty of the model and somehow eliminate also this problem.
Yeah, what you just said.
Okay, thank you very much. We are